Hi, my name is Kevin Cohen. I'm the director of the Biomedical Text Mining Group at the University of Colorado School of Medicine. And today I'm going to be talking to you about how to review the results section of a paper about data science, machine learning, or natural language processing. This is joint work done with my colleagues Karen Faure, Margot Miskas, and Aurélie Beviol. We're going to talk about results sections because they're a nearly universal part of any paper in our field. It'll be very unusual for you to be asked to review any paper that doesn't have a results section in it. The typical elements of a results section are pretty standard across conferences and across journals and paper types. They'll usually contain tables and/or figures, and those tables or figures will convey values and relationships between values. And then a good results section will also have an error analysis. One of the things that I like about results sections is that when you're reviewing them, this is often the place where you can be the most helpful to the authors in helping them improve their paper. For example, let's do a quick exercise. We're going to look at two comments that a reviewer might write, and you're going to tell me whether they're strengths or weaknesses of the paper. Feel free to take a moment to pause the video right here and look over the two examples of things a reviewer might write. So you've had a moment to look those over. Let's talk about the first one. So in number one, the reviewer writes, the assertion that the system achieves state-of-the-art performance is only supported by a single figure of merit. Well, the only in there tells you right away, this is a weakness of the paper. Now the reviewer goes on to write, see Empirical Methods for Artificial Intelligence. That's a book by Paul Cohen that if you haven't read, you should. For why this is an important weakness of the paper. So here you're being helpful to the author in pointing them towards something that will help them to address the weakness that you've identified. Let's look at number two. The assertion that the system achieves state-of-the-art performance is supported by multiple metrics. See Empirical Methods for Artificial Intelligence for why this is a strength or weakness, of course, a strength of the paper. Now here, you're also helping the authors. What you're helping them do is explain better why they measured multiple metrics, why they reported multiple metrics, and how they can use that to strengthen the claims that they make in the paper. Another thing that I like about reviewing results sections is that they're mostly straightforward. You can put together even a checklist for how you do them. Mine looks something like this. First, I'm going to ask if the metric is appropriate for the task. For example, accuracy is very rarely an appropriate metric in data science, machine learning, natural language processing. Many kinds of tasks have metrics that are commonly used to assess them. And a benefit of using those common metrics is that it helps to make it possible to compare results about papers. On the other hand, a novel metric for evaluating something can in and of itself be a really nice contribution of a paper. Another thing that I'm going to look at is baselines. Number one, there should be some baselines. Number two, they shouldn't be trivial. And there's a number of things here that we'll talk about in just a little bit further on in this tutorial. So one of the things on our checklist is this idea. When people report a measure of central tendency, that's a mean, a median, or a mode, they should always be reporting at the same time a measure of dispersion. Pretty much the only time that you won't see this, or that you don't need to see it rather, is when someone is doing their evaluation on a single blind test set. If you're seeing something like evaluation by cross-validation, if you don't remember what that is, no problem. Just remember that it's a way of evaluation in which you take multiple measurements. You can report the mean if the data is normally distributed, or the median, but you need to have a measure of dispersion that goes along with that. And there are typical ones for the different measures of central tendency. Let's go look at another set of possible reviewer comments. And I'd like you to take a moment, read these over, and ask yourself, for each of these reviewer comments, is it describing a strength or a weakness of the paper? So you've paused your video and thought about that for a moment. Let's talk about the first one. Here's what it says. The reviewer has written, the work is evaluated via cross-validation, but does not report measures of dispersion. Without those measures of dispersion, it is difficult to have confidence in the stability of the results. Well, clearly, the reviewer is describing a weakness here. What I like about the comment that the reviewer has written is that they're explaining why this is a weakness. Let's look at number 2. The work reports measures of dispersion, which increases confidence that we understand the stability of the results, or lack thereof. And what I like about this is that the reviewer is explaining why this fact that the authors reported measures of dispersion, in fact, is a strength of the paper. And think about this, these are things that the author might add in the case of a strength. They might tell you why they reported the measure of dispersion and what they would like you to take from that. For example, that the results are stable, or if they're not, that's a finding too. In either case, you want the paper to tell you what the measures of dispersion are for whatever those measures of central tendency were. And this is true even when there's no hypothesis test. You're probably used to thinking about things like measures of dispersion when you see a hypothesis test used. But that's not the only time you want them, because measures of dispersion are not only relevant to thinking about whether or not two sets of results are statistically significantly different. They're also very important for thinking about stability. So how much does that measure of central tendency really tell you about what you could expect from this system if you threw one more set of test data at it? Another important thing to look for in a results section is that the appropriate hypothesis tests are done. For example, it's very common to use parametric hypothesis tests, but they're not always the appropriate test for the data that's being looked at. For example, if you're using a parametric hypothesis test, then you need to know that the data on which it's being used is normally distributed. So for example, if you have a paper that's using a t-test to evaluate differences across two sets of cross-validation runs, then the paper needs to show the reader that the data is normally distributed. They might do that by showing you a graph. They might do that by reporting the results of a Shapiro-Wilk test, the test for normality of distribution. But in some way, it should show the reader that indeed that parametric test was the appropriate one. Let's look again at a little exercise. Pause your video for a moment and think about this, and then start it up. So you've paused your video and thought about this. Again, we're going to look at two reviewer comments, and you're going to ask yourself, is the reviewer describing a strength or describing a weakness of the work? So reviewer comment 1, The work is evaluated by a statistical hypothesis testing using a parametric test, but does not demonstrate that the data is normally distributed. Now, the but in there right away tells you this is describing a weakness of the paper. If you want it to be helpful, and I do suggest that you be helpful, say why that's important. Number two, the work demonstrates that the distribution of the data is appropriate for the hypothesis test. Here we're clearly describing a strength. And if you want to be helpful to the authors, explain why that's a strength, and maybe they'll put that extra bit into the paper so that they can help the next reader understand what's good about their paper. So again, one of the things that's nice about reviewing a results section is that they're pretty standard. And so you can develop systems of your own, like the checklist that I showed you for going through a results section. For example, it's very useful to develop a system that you use anytime that you look at a graph. For example, you might already have the habit of always looking at a graph from left to right and top to bottom, looking at the axes and then looking at the quadrants. And when you're looking at the axes, you're probably looking at things at a minimum, like, are they labeled? Does the paper tell you what's on those axes? And are they or are they not truncated? Truncated means that you have reduced from the full range of the value that could be on that axis. It's most commonly seen in situations where people are trying to talk about performance and they want to make either make numbers seem artificially better than they are, or make two things look more different than they are. Let's look at some examples. So think about these graphs right here. Let's do our little let's do our little left to right, top to bottom, axes to quadrants. So looking at the figure on your left, looking at the y-axis to the left, we see that the range is from 0 to 1, and what's being graphed there is precision. That's great. You want your y-axis and your x-axis to cover the full range of values for that metric, and the range of values for precision is 0 to 1. So we know the range, we saw that it's labeled. Now we'll look at the x-axis, and we see that it's labeled. Recall is being plotted. We know that the range for recall is 0 to 1, so we want to see that as the range there, and sure enough, when we look at it, the range is 0 to 1. Now we look from top to bottom, and we see that the graph is clearly labeled. We know that it's cross-validation results, so a priori, from the beginning, we know that we expect to see a series of points. So we look at the quadrant and we see that indeed we have two kinds of points. We have the open circles and the open triangles, and we see that they're overlapped some and mostly cluster in the same part of the graph. Let's look at the next one. Now, starting with the axes, left to right, we see that the label on the y-axis, there is a label and it is precision. So that's good, we have a label. Now we look at the range and we see, oh, that's not so great. It's 0.7 to 0.9. So the authors have taken the full range from 0 to 1 and they've truncated it on the top and the bottom. So they drastically reduced the range, not good. Now we look at the x-axis, it's labeled and it's got recall. So we know that the range for recall is from 0 to 1, and that's what we would expect to see as the range. Oh, that's not so great either, because they've truncated that range of 0 to 1 to 0.7 to 0.90. Now, top to bottom, We see that the graph is clearly labeled, cross-validation results. And so again, we're going to expect to see the same kind of thing. We'll expect to see probably points for two different systems, and the points that are open circles are there, points that are open triangles are there. Certainly we hope that in the caption to this figure, the paper tells us what the open circles and the open triangles are, but we'll leave that aside. Now I want to ask you a question. Which of those graphs shows the best results? Pause your video for a second, think about that, and then start it up again. So if you've looked at those and asked yourself which shows the best results, you've probably realized that they show the exact same results. So to make these two figures, I had the exact same data points, but I truncated the axis on the one, excuse me, to your right, but not on the one to your left. What's the effect of that? Well, by truncating the axes in the graph on the right, I've made it seem as if there's a pretty good separation. So you see here a little bit of overlap between the open circles and the open triangles, but not very much. An author who is using the graph on the right is hoping that you will accept that there actually is a performance difference between these two systems, maybe a difference in the means. And they want it to look like a big, clear, obvious difference. Well, if you put that on the full scale, it's not such a clear difference after all, actually, is it? So this is a case where the paper is trying to claim a difference between the two systems, but it's not so clear that there is one, or if there is one, that it's large enough to actually be meaningful in any way. So another thing, that I've said that I like about reviewing results sections is that it can be really helpful. It's easy to be helpful to the authors. So how might you be helpful to the authors here? You might point out to them that the paper could be improved by putting the real ranges on the axis of the one to your right. Axes, sorry. So another way to be helpful to the authors is to help them choose when to use a graph and when to use a table. This is exactly that situation. So if we go back to those graphs, what we see is that the author is hoping in that table to the right, graph to the right, to convince us that there's a difference in something like the means. Now, this is a point that actually is not made very well with that graph, because as I said, as soon as you see the truncated X and Y axes, you should think, wait a minute, time out, there's a problem here. When the point that you're trying to make is about the exact values, and that's probably what that author was hoping to do, to convince you that the means of the cross-validation results of the two systems were different, this is a place where you want to use a table. And that's a rule you probably already know, but it's helpful to point it out to the author. When the actual values count, a table is what you want. Let's do another little exercise here. And I want you to answer the question, is this figure a good figure, a bad figure, or neutral? So pause your video for a moment here and think about that. Then start the video up again when you can tell which it is and explain why. So you've paused your video and thought about that. Let's try our little scheme of look left to right, look top to bottom, look at axes, and then look at the quadrants. So we start at the left, and we don't see any label on that axis, actually. That's a down point right there. Then we look at the range of values, and it's 0.979 to 0.982. Well, we can guess right here that this is probably a metric in the range of 0 to 1, and this paper truncates like crazy on that y-axis. The only time somebody does this is if they want to convince you that there's a difference that's not really there. And I actually have seen pretty much this figure at an Acoustical Society of America meeting, and that's a pretty good conference. So my point being, this does happen. All right, starting at the left, we looked at the y-axis, no label, and horrible truncation of the range. Going from top to bottom, it's not labeled, that's not good. And going to the x-axis, such as if we can talk about that in a bar graph, we see we have two things graphed and they're not labeled. We don't know what we're looking at here. So this is a place where you could be very helpful to the authors by telling them the basics of how to draw a graph like that. As a little secret here, that's something that you can write in a review template and just cut it and paste it every time that you need to lay that out for an author. Great way to be helpful as a reviewer. Another little exercise here. The point we're making is that graphs need to be clear to have a result section that actually sends the reader a message. So here is a graph that I took off of the mathworks.com website. You can see the address of it. And I want you to stop the video for a moment and ask yourself how many dependent variables are being graphed here. I will join you. All right, you've paused your video and thought about that. Let's look at our figure now. And I'm going to assert that there are 3 dependent variables being graphed. Dependent variable means what the experimenter controlled as opposed to what they measured. That's the independent variable. So this is my analysis. My analysis is that, excuse me, they have one independent variable is what group do you belong to? So there's a test group, group 2, 4, 6, 8, and -1. Personally, I don't know what that means. You hope that the caption to this graph explains that. But there's one dependent variable. Second dependent variable is whatever is being indicated by the bars within each group. So if we look at group test, 2, 4, etc., we see that each of those groups is made up of 3 bars. What do they mean? I don't know. Hopefully they tell us in the caption. And then the third dependent variable, whatever it may be, is indicated in those stacks. So when we see the stacks, they go from dark blue to light blue to yellow to red. In some way, those stacked things represent a third variable. Now, here's what I'd like you to think about this. If a reader can't even easily tell how many dependent variables are being graphed, then the reader might not be able to get anything at all out of that bar graph. So your helpful comment to the authors here is to say something along the lines of, that figure is really difficult to interpret. So you might, depending what's actually in those dependent variables, you might want to recommend a different kind of graph. You might want to recommend tables versus figures. Right? I'm not going to go into details about tables, but here again, clarity counts. So this is a real table that I got from the website you can see there. Feel free to go there and look at their examples. If you want something more in-depth, I've given you the name of a book by Matthews and Matthews that has a very nice section on tables as well as on graphs. It's actually a very good book overall, and I recommend it. All right, a little exercise to keep us awake. Again, we're going to look at these two reviewer comments, and we're going to ask ourselves, are they describing a strength or a weakness of the paper? So pause your video here for a moment, think about it, and then start it again. So you've thought about this. Let's talk about them. Number one, the paper does not specify whether or not the hypothesis test is directional, making it difficult to determine whether or not the hypothesis testing is reasonably conservative. Now, this points out a true weakness that a paper could have, and it also explains to the authors what they might do to make the paper better. So, for example, in this case, maybe they'll say something like, we had a directional test because there's an a priori expectation that one value will be higher than the other. Or maybe they'll say, we used a non-directional test with less power because there's no reason to have a priori expectations. Let's look at number two. The paper explains how the hypothesis test is the appropriate one for this experiment. If that's true, it's a real strength for the paper, actually, that often gets omitted. And this is a comment that might not change what the authors do, but it's a big help to an area chair and or to a conference program chair in deciding whether or not they should accept this paper. I'm going to talk very briefly about a couple of things to watch for in the results. And although they're serious, I'll only talk about them briefly here because they're covered at more length in the video on reviewing the methods section. So thing number one, watch for confounds. A confound is something that could be an alternative explanation for the results that you've seen. And I'm giving you here references to 3 papers that talk about things that could be confounds. So suppose that you're comparing 2 systems and they use different tokenizers. That alone could be the cause of the performance difference between them, or let's say the behavioral difference between them. Relationship between 2 sets of outcomes in an experiment could be due entirely to the amount of training data available. It might not hold at all for a different amount of training data. So keep an eye open for these. Also, watch for poorly designed experiments. So think about something like an ablation study, where you look at an entire set of features versus just some of the features in that system. I'm going to show you a bad one on the left. Here we're looking at 2 different feature sets where we have an F1 measure for word embeddings alone and word embeddings plus bag of words. And what you would often see from a bad ablation study like that is the paper concluding that bag of words don't do anything as a feature since they don't add anything to the score that you get from word embeddings alone. Let's look at a good version of that ablation study. So there we have an F1 measure for word embeddings. We also have one for bag of words alone, and then word embeddings plus a bag of words. What we see there in that set of results is actually word embeddings are fine, bag of words is fine. If you left out just the top row of that, you could imagine the paper concluding that actually it was word embeddings that didn't add anything to what you did with the bag of words. So the point here is in a good ablation study, you want to see every feature can not just ablated, not just removed, but all features but one ablated. Or in other words, you want to see every feature alone. Finally, watch out for over-optimizing. I often think of this in terms of a quote from Thomas Edison: "I have not failed. I have just found 10,000 ways that don't work." Well, you could imagine a lot of papers that rely on having achieved a particular performance level for their claim to have done something as being rephrasable this way: I have not failed. I've just found 9,999 ways that won't work and one that does. That's not much of a paper. Notice that there's something I have not talked about in here that you might have thought I would have, and that's performance. There's been no point in here at which I've suggested that the question you should be asking when you look at a results section is, how good was their F measure, or whatever it is they're measuring in their evaluation. And the reason that I haven't talked about it is because how well they did or didn't do some task has nothing to do with the quality of the research that went into getting those numbers. Think about it this way: if all that mattered was how well someone says they performed and not how they got those numbers, then you would buy any car that someone told you was a good car. You wouldn't think, well, okay, you're telling me it's the fastest car on the market, but it costs $80,000, so I'm not going to buy it. You should be thinking in the same way about research as you would think about the question of whether or not you would buy a car based on the information that an advertisement is giving you, a salesman is giving you, or the research paper is giving you about the experiments that were done in the evaluation. And this creates a problem. The habit that you see in many reviewers of just looking at performance and whether or not it's better than somebody else. The problem is called publication bias. Publication bias is a tendency to publish papers that have positive results and not negative results. And in the context of machine learning, natural language processing, data science, what positive result typically means in practice is that it's claimed that some system outperforms some baseline or some other system. Publication bias is a problem because it distorts the true state of the field. In particular, if all that gets published on some topic is papers that say, this worked better than something else, then you get the impression from reading the literature that that is really great. And what you don't see in a situation of publication bias is all of the experiments where, in fact, that didn't outperform them at all, and your grad student says, oh, I don't know what I did wrong. You know, neural nets were supposed to be the best for this, and they're not at all. Well, that doesn't mean you did anything wrong. You may have discovered a weakness in neural nets, taking that just as an example. Here's how this can distort the true state of the field. Imagine a situation where, because of the tendency to only publish positive results, defined as some system outperforming other systems, you end up with 25 papers one year that report that deep learning outperformed any other approach. And in that same year, you have 0 papers that report that deep learning did not outperform any other approach. Deep learning looks wonderful now, right? Compare that to what the state of the field looks like without publication bias. Here you have those same 25 papers published that report that deep learning outperformed every other approach. Maybe you also have 25 papers that report that deep learning didn't outperform any other approach. Maybe you have 50 papers that report that sometimes deep learning outperformed other approaches, sometimes it didn't. It outperformed some approaches. It doesn't outperform others. Now you have a very different picture of, of deep learning and how well it does or doesn't work on problems in our field. Why I'm talking about this in the context of results section is that reviews of results sections are where publication bias primarily plays out. So you may have gotten papers, reviews yourself that say something like, performance is not state of the art, therefore I'm giving it a low score. That's a terrible review in and of itself, because whether or not the results are state of the art has nothing to do with how good the motivation for the paper was, how innovative it is, how significant the problem is, how well designed the experiments are, and the extent to which they do or don't support the conclusion. Those count. Having those reflect good science in a good paper. Whether or not you have the best performance, the state-of-the-art performance, it has nothing to do with the quality of the paper. And this works out in two ways. One way that publication bias works out is rejecting papers that don't have state-of-the-art results, even when they have interesting findings. Another way this works out is a bias towards accepting papers that do report state-of-the-art results, even when the paper itself is otherwise deficient. Like I said, if you wouldn't buy a car on the basis of a salesman who didn't tell you anything more about the evaluation of that car than this paper told you about how the study was done, you probably shouldn't recommend acceptance for that paper. How do we do this? Overall, we should think about the validity of the work that's described and not about their performance. Let me describe to you two ends of a spectrum of how we could review. On the left is what I'll call the leaderboard model. And in this case, we see one thing and one thing only. The name of the team who did a classification task, think of that as the authors, and then their score. Here, on the leaderboard model, we knew nothing about what they did. All we know is they did the best. Does that have any value? Probably not, actually, not to science. It might let you write an advertisement, it might let you write marketing materials, but it doesn't tell you anything about the quality of the research. And I want to point out that smarter people than me have given this example of the leaderboard model. Ken Church, Christopher Manning, Bonnie Weber. Sorry, Bonnie, for that question mark behind your name. You have pointed this out. On this model, your submission to ACL could just be a letter saying, I achieved an F measure of whatever on some task. Who needs the paper in that case? Compare that with a paper that has no results in it at all. Let's look at an example here. I'm showing you a table and its caption from a paper of mine. And what you can see from that table is that I did a number of experimental conditions. The columns reflect 3 different sources of data that I used. That's the GOA curated, NLP abstracts, and NLP with full text. You don't even know, you don't have to know what any of those mean to know I looked at 3 different experimental conditions. When you look at the rows, those show you results for 6 different classifiers. You don't even need to know, frankly, what I'm classifying to know that I tried pretty hard to see what the performance was across variation, not just in data sources, but also in classification approaches. And then from the 2 groups of rows, you can see I looked at unbalanced and balanced training data. So you know there's yet another independent variable in here. So you know I had a pretty good experimental setup there. What the performance was for any of those, that's not relevant. I'm going to be able to tell you something from whatever those results are about whether there is or isn't an effect from balance in the training data, and if so, what it is. I'll be able to tell you if there is or isn't a difference across the data sources, regardless of whether there is one or not. I'll be able to tell you whether there is or isn't variation across classification approaches. From all of that, I ought to be able to tell you something I've learned. And that's totally independent of what the numbers are in those on that table. And I have to give credit for this idea to Catherine Button et al. And a wonderful paper of theirs called Preventing the Ends from Justifying the Means, Withholding Results to Address Publication Bias and Peer Review. Very nice paper. I recommend you take a look at it. So never write this in a review. Does not report state-of-the-art performance. Why not? Because it's irrelevant. In the end, it has nothing to do with the quality of the paper, one way or the other. I'll give you a quote from Kenneth Church on this. The better the numbers are, the more important it is to reject the paper. We can't afford papers that report results without insights. Where do the insights come from? They come from experiments like I'm showing you here in the de-resultified model side of this slide. Now, given how much time we spend fighting for those ever elusive state-of-the-art results, I think Kenneth Church's statement here is going to be pretty surprising to a lot of people in our field. Surprising, and it's true. Okay, cut here. So I want to give you a couple of exercises as we get towards the end of this. And this is a longer one, so I won't ask you to pause your tape here, but do think about this as you go forwards. So we know that the Association for Computing Machinery has a code of ethics and professional conduct, and that it talks about this, the responsibility to give comprehensive and thorough evaluations of computer systems and their impacts, including analysis of possible risks. So think about, what does comprehensive and thorough mean in the context of a paper that's claiming to have state-of-the-art results on some task? If it only shows the baseline and the best run, is that comprehensive and thorough? Or is there more data that you have to give to see what comprehensively what the performance of that system is actually like? It's the difference between telling you the speed of a car on a racetrack and telling you how well that car will operate on city streets, in mud, in snow. And which of those do you really care about in the end, right? A nice question from a chapter by Philip Resnick and Jimmy Lin. Take some time to come back to this and think about it. So I started out by telling you that one of the nice things about a results section is that we can work off of a checklist to do it. to evaluate it. Reviewing a results section is pretty straightforward. And if you look at this list, you'll see there's nothing on there that says, look for a bolded line that gives the highest performance in some row. I want to refer you to some useful readings on the things that we've talked about in this tape. Here's a bunch of papers on publication bias. The first one is the one by Catherine Button et al. That I mentioned. There's others from Kenneth Church, as I mentioned. Also, Christopher Manning has talked about this kind of thing. Bonnie Weber has talked about this kind of thing. There are also, there's a couple of books, one by me and a number of colleagues who I will name in a bit, on how to review a paper about natural language processing, and one from a book by me on how to write about data science research. And then finally, there's a book by Paul Cohen, who is not me, called Empirical Methods for Artificial Intelligence, and a wonderful piece by Ted Peterson, which I'm very sorry I did not get onto its own bulleted point, called Empiricism is Not a Matter of Faith, about the importance of having code available, especially in papers whose whole claim is, we did the state of the art on something. Number of very good pieces on why you should not just be thinking about performance when you review a results section. The one by David Hand is a classic. There are also some papers in here by people in natural language processing, Chris Manning, Mark Steedman, Stephen Wu, Bonnie Weber. These are top names in our field. And if you don't believe it when I say it, you should believe it when they say it. And then finally, some work on statistical significance. Usually a results section is where you see claims about statistical significance or the lack thereof. And one nice thing about recent years has been some papers coming out specifically on statistical significance in natural language processing research. Everything in this tutorial shows up in a book by me and my colleagues Karen Faure, Aurélie Nevéol, and Margot Miskas, called How to Review a Paper About Natural Language Processing. You can find it available for free in a number of places. And finally, I want to point out once again that this tutorial is jointly work with the colleagues that I just named. So thanks for your attention.